When you see a tornado, it's easy to just think of it as pure random chaos, right? A force of nature so powerful it can literally rip a house from its foundation. But what if I told you that behind all that terrifying power, there's actually elegant physics, beautiful math even? So, in this explainer, we're going to dive right into the vortex and uncover the real science of tornadoes. Okay, let's just start with a number to set the stage here: 200 miles per hour. I mean, think about that for a second. That's faster than a Formula One car at full throttle. We're talking about wind speeds inside some of the most violent storms on our planet. And that's the kind of power we're about to break down. And this right here is really the core idea for this whole explainer. That destructive force you see on the news, it's not just random mayhem. It actually follows a set of rules. Now, they're incredibly complex, for sure, but they are predictable. And understanding those rules, well, that's the key to predicting and surviving these incredible storms. All right, first up, let's look at how this incredible engine of nature is even built. To really get a handle on the storm, we have to understand its parts, starting with the fuel that gets the whole thing going. And honestly, the best way to think about it is kind of like a recipe for the perfect storm. You can't just throw these ingredients into a bowl and hope for the best. Nope. For a tornado to actually form, you need a very specific set of atmospheric conditions to come together in exactly the right way. So, what are those key ingredients? Well, here they are. First, you need moisture, a lot of it, usually coming up from the Gulf of Mexico. Then, you need instability. That's just a fancy way of saying you've got warm, moist air trapped underneath colder, drier air, and it really wants to rise. Third, you need lift, something to kick it all off, like a cold front. But there's one ingredient here that's more important than all the others. And that secret sauce is wind shear. This is the absolute game changer. All it is winds at different heights, blowing at different speeds, or even in different directions. And here's the thing. Without wind shear, you just get a regular old thunderstorm. But with it, well, that's when you get rotation. So how does that even work? Okay, picture this. The wind shear creates this invisible tube of air that starts rolling along the ground, kind of like a giant invisible log. Now, when a thunderstorm's powerful updraft, that rising air we talked about, sucks that rolling tube up, it gets tilted. It goes from horizontal to vertical. And just like that, you've turned a simple roll into a terrifying vertical spin. And that huge, rotating column of air, it's got a name. It's called a mesocyclone. Think of it as the parent of the tornado. It's this massive, spinning vortex inside the thunderstorm. We're talking miles wide sometimes. It's the giant powerhouse that a smaller, much more intense tornado can drop out of. Okay, so we've got our rotation, we have the mesocyclone, but how does that spin get so ridiculously fast and destructive? Well, the answer lies in a fundamental law of physics that, believe it or not, you've probably seen 100 times without even realizing it. Just think about an ice skater, right? They start spinning with their arms way out, and then what do they do to go faster? They pull their arms in tight, and bam, their spin speeds up, like a lot. A tornado works on the exact same principle. It's just doing it with a massive column of air instead of arms. Now, the official sciencey name for this is the conservation of angular momentum. All it means is that as that wide spinning mesocyclone starts to tighten up and stretch down into a narrow tornado, the radius of all that spinning air gets smaller and smaller. And to conserve its momentum, its speed has to increase. It has to skyrocket. That's the physics that gives you those insane 200-mile-per-hour winds. And hey, for anyone who wants to peek under the hood, this is the master code behind it all, the Navier-Stokes equations. You can think of them as the operating system for how fluids, and remember, air is a fluid, move. Now, we are not going to try and solve these, don't worry. But the big takeaway here is that even something that looks as wild and chaotic as a tornado is, at the end of the day, governed by a set of mathematical rules. But you know what? The spin isn't the only weapon in a tornado's arsenal. Check out this number. That represents the pressure drop that can happen right inside the core of a tornado. We're talking a drop of up to 100 hectopascals. And a pressure drop that big, well, it creates an incredibly powerful effect. And that effect, that's all thanks to something called the Bernoulli effect. Basically, those super high wind speeds create a pocket of extremely low pressure right in the middle of the tornado. This huge pressure difference between the inside and the outside of the funnel, well, that's what turns the whole thing into a massive atmospheric vacuum cleaner, just sucking everything up into the vortex. All right, so we've covered the theory, we've seen the physics. Now let's see what happens when these principles get pushed to their absolute terrifying limits out in the real world. It's time to meet some of history's most monstrous storms. And what's crazy is that tornadoes can be monsters in totally different ways. You've got the Tri-State tornado back in 1925, which carved the longest path in history. Then there's the Joplin tornado in 2011, the single costliest one ever. And then get this, the El Reno tornado in 2013. It became the widest tornado ever recorded, a terrifying 2.6 miles from one edge to the other. Just imagine that. I mean, these storms are just terrifying. But science isn't just about explaining them after they happen. The real goal is to spot them before they strike. So how do we do that? How do we actually see inside a giant thunderstorm to know if a tornado is about to form? Well, our primary tool for this is advanced Doppler radar, specifically something called dual polarization radar. Now, this tech is amazing because it doesn't just see rain or hail. It can actually tell us the shape and the size of the things its radar beam is hitting. And that provides an absolutely crucial clue. So what meteorologists are looking for is something they call a correlation coefficient drop, or just CC drop for short. Here's how it works. Raindrops are all pretty much the same shape, right? They're uniform. So when the radar beam suddenly starts hitting a whole bunch of objects that are all different shapes and sizes, totally not uniform, that CC value just plummets. And there is really only one reason for that to happen. That CC drop, that's the signature of what forecasters call the debris ball. It is the smoking gun. It's the radar telling them, hey, I'm not hitting raindrops anymore. I'm hitting pieces of houses and trees and dirt. It's undeniable proof that a destructive tornado is on the ground doing damage right at that moment. And you see, it all comes back to this one idea. From understanding the physics of wind shear to being able to read the signature of a debris ball on radar, our knowledge of the science is what gives us a shield. It's how we turn all this raw data into life-saving warnings, giving people precious seconds to get to safety. So we've unpacked the beautiful, orderly science that's hiding behind one of nature's most chaotic-looking events. And it really leaves you wondering, doesn't it? If we can find the equations that govern a tornado, what other terrifying forces of nature, hurricanes, earthquakes, you name it, can science eventually help us understand, predict, and maybe, just maybe, one day,